Hello, this is the week 3 lecture video for chapters 5 and 6 in astronomy on radiation, spectra, and telescopes. Let's get started. So we see here our sun. This is an ultraviolet light. We normally see it in visible light as a kind of a yellow-orange star. It's actually a dwarf star, cool in temperature. But compared to the nearest stars, it's actually more of a bigger, brighter star. So James Clerk Maxwell unified the rules governing electricity and magnetism into a coherent and one unified theory. We can make waves in a pool of water by creating a disturbance. So here's how we describe a wave. A wave has a crest to it, a top part, a trough, a bottom part, and the period of time interval between two crests or two troughs is called a wavelength. So from one top through the bottom and into the next top, that is called a wavelength. The number of cycles that goes through that period during a certain amount of time is called the frequency. Now we have this law called the inverse square law for light. And it says that if you double the distance away from a luminous object, you will make that object appear 1/4 as bright. So it's the inverse square law, 1/4 as bright. If you triple it, then the inverse of 3 is 1/3. You square that, 1/9. It's 9 times fainter if it's 3 times farther away. So this diagram just shows the bands of the entire electromagnetic spectrum that goes all the way from short gamma and X-rays to the longer microwave and radio waves. And we can see that on Earth we get visible light. Of course, we can see that with our eyes. We get a little bit of ultraviolet, quite a bit of infrared. In fact, my studies in college was in the infrared part of the spectrum because I studied cool stars. We needed to detect the heat from those stars. And we do get a lot of radio waves, but everything else is opaque to our atmosphere. The water vapor absorbs it. So if we want to study in the gamma rays, X-rays, most of the ultraviolet, even into the microwaves, then we would need to send space telescopes into space. Or we have a orbiting spacecraft called Sofia that looks above the water vapor and most of the atmosphere into the infrared. So here's a map of the sky, the entire sky that we can see in X-rays. And in the middle, there's a lot of brightness here, and this is due to the black hole that's in the middle of our Milky Way galaxy. So we have some laws that dictate radiation. And so this shows that hotter temperatures will peak at more shorter wavelengths. So if a star is blue, it's very hot. And it's going to be seen in the visible, of course, but it also could be seen in the ultraviolet. If a star is red, then that means it's very cool temperatured. And so its peak radiation temperature comes right at about 3,000 degrees Kelvin, and that's seen in the infrared. Remember where I just told you that I studied cool eclipsing binary stars. They were red dwarf stars, and I used the infrared spectrum to see them. Now we can split up how a star and its light appears to us by two methods. One is a prism. Here we have a prism that white light comes into and it diffracts. the light into its component colors. Red is at a measurement of 760 nanometers, that's billionths of a meter. Violet is at 380 nanometers, and this is a very small spread of space through the entire electromagnetic spectrum. We can also use what's known as the diffraction grating to look at this spread out light, and that's preferable. So let's take a look at spectra. A continuous spectrum looks like a rainbow. It goes all the way from the ultraviolet to the infrared with the visible in between, and this is a continuous spectrum. So a visible part of the spectrum of the sun looks like this. This is actually an absorption spectra. So absorption spectra occurs when you have the light from a hot object, the sun, coming through cooler atmospheres like the sun has, and that cooler atmosphere absorbs some of the light rays. And so we can detect what chemicals make up the sun and at what temperatures by where these dark lines you see here appear at. And this is called an absorption spectra. On the offhand, in rare cases, we can get emission spectra. So we have continuous spectra is the whole rainbow. Absorption spectra are just dark lines in the rainbow, and that's what 90% of all stars are absorption spectra stars. But a few rare kinds like white dwarfs that are very hot and dead will show us emission spectra. And they show us their own lines. And each element has its own set of lines. We have the double K lines in sodium. We have Balmer lines in hydrogen. We have the H and K lines in calcium and mercury. So this is what causes a rainbow. And when you only have a double rainbow, like we see in picture B here, that means there's a lot of scattering going on. Now, as an offshoot, I can tell you I'm in Springfield, Missouri, and in 2011 we had the very deadly and disastrous Joplin, Missouri EF5 tornado. In that tornado, there were 161 lives lost, but there was also 20,000 buildings that were thrown up into the sky, and that debris scattered the light all the way from 70 miles away in Joplin to Springfield, and I saw the most brilliant double rainbow I have ever seen in my life. I knew at that moment that I needed, as a meteorology professor does, along with astronomy, needed to get to Joplin, Missouri immediately. So we have this famous double slit experiment with Rutherford, where we have a piece of thin gold foil with two slits in it, and we sent a beam of alpha particles towards it. This is a radioactive source, and we got some beams coming out of it on the other side. The hydrogen atom can be made up of protons in the nucleus, neutrons in the nucleus, and electrons orbiting around it like a planetary orbit would be. And so this is called the planetary theory of atomic nuclei. So in helium, we have two protons, two neutrons, and then electrons going around it. The two protons and two neutrons both hold much more mass than the little tiny electrons going around it. Now, if you add an extra proton to the mix, we can get different isotopes of an element. And so we have the regular hydrogen. If you add an extra one to hydrogen, we get deuterium or tritium. extra neutrons. Niels Bohr and Max Planck worked together to show the energy behavior of photons and come up with this planetary model of the atom. And so in Bohr's model of the hydrogen atom, we have these electron levels where only a certain number of electrons can inhabit an orbit. And so for different orbits, different number of electrons can be seen, and we see different spectra depending on how many electrons are in these orbits. And so for hydrogen, we have these different series of energies involved with electrons. So here to summarize the three types of spectra, continuous spectrum is a hot glowing object with no atmosphere around it. A bright line is a hot glowing object with no atmosphere, nothing to keep the spectra from being disturbed. But most stars, 90% of them, are of this continuous spectrum with dark lines called the absorption spectra. And where these dark lines line up in the color and in the nanometers tells us the chemical composition and also the temperature of those stars. Here's one of my favorite constellations. In fact, I just recently got a new dog. I rescued him from a puppy mill and I named him Orion. And the reason I did that is because my favorite constellation in the entire sky, winter or summer, spring or autumn, is the big hunter Orion. And right here we have the belt of Orion, 3 stars in the middle, and straight down from the middle star there is a gaseous nebula there called the Orion Nebula. And right there I have studied some eclipsing binary stars right there called BM Orionis as part of my undergraduate career. And so in this description here we see both the visible spectrum, we see X-rays, and we see infrared. And most of this gas is infrared, and that's what made it so hard to study the star BM Orionis, this eclipsing binary star, because it had a lot of gas and dust around it. And when you study these kind of stars, you need a very black, dark background to compare it to other stars that have a completely dark background. And so my star, BM Orionis, did not have that, had all this gas involved in it. We go on to chapter 6, and here we have telescopes. And these are 2 prehistoric telescopic observatories. Machu Picchu in the 15th century Incan site of Peru, and Stonehenge, a prehistoric site in England. So in a refracting telescope, we have lenses. And so in a simple lens, white light comes into the lens. It's curved at both sides or one side, and that light is bent towards a focal point called the focus, or focal point. That distance between the lens and the focal point is called the focal length, and that's a very particular characteristic of that lens. So in a refractor, we have lenses that bend the light to our eye. In a reflector, we have starlight coming into a mirror curved in a particular way, depending on what kind of reflector telescope it is, to our eyes. Some of them come out the side like this, Newtonian. Some of them come out of a mirror flat right here, back into the mirror where there's a hole, and that's called a Cassegrain focus. So that's why I was just showing you here the prime focus. Newtonian focus comes out of the side, and the Cassegrain focus comes out of a flat mirror through a hole in the middle of the mirror, primary mirror, down to our eyepiece. And that's the kind of telescope that I have used personally most of my career. So here is one of the large primary mirrors of the European Southern Observatory's very large telescope. And so they can coat it with aluminum or gold. That'll be on the James Webb Space Telescope. And this mirror is 8 meters in diameter. And for feet, that's about 40 feet across. You can see the human being here. You can see the size of that mirror. This is a very, very precisely clean room. So no dust particles gets on that mirror. And so here are some modern reflecting telescopes. The Palomar 5 meter in Los Angeles, on top of Palomar Mountain, right here on the left. And the Gemini North and South 8 meter telescopes. There's one in Hawaii, there's one in Chile, operated by the same consortium that I worked with, the National Optical Astronomy Observatories. So how can you make a big telescope even bigger? Well, the mirrors need to be made of glass. But glass is very heavy if you make it big enough to support a mirror on a telescope. So instead of making one humongous 10 meter or 400 inches wide mirror with a thick enough glass that would have to be feet and feet thick to hold that mirror up, you can make segments of a mirror. And so this is the Keck Telescope in Hawaii, one of two, and it's made up of segmented mirror segments coated proportionally. And so they put these all together to make up one big mirror. And on the back side of each mirror are actuators that move up and down to compensate for the disturbance of the atmosphere, the seeing effect, or the flickering or glimmering of starlight you might see as twinkling. So George Ellery Hale worked to build the 40-inch refracting telescope at Yerkes Observatory, that's in Chicago, and also the Mount Wilson Observatory and the 200-inch Hale telescope at Palomar Observatory outside of LA. And so there is a physically limiting size to how big you can make a lens, and it is about 40 inches or about 1 meter. And this is the Yerkes telescope that Hale made in Chicago, and you can see this is 40 inches across, or 1 meter about, but you can see how long this telescope has to be able to make a focal length on that mirror. Now we like to put our biggest and best telescopes high and dry on top of extinct volcanoes away from city lights. And so this is in the Atacama Desert in Chile. This is Cerro Paranal, a mountain summit. It has several 8-meter telescope buildings and a 4.1 meter telescope off here in the distance. You can see there's nothing around, so no light disturbance gets involved. Now the power of adaptive optics. This is what I was telling you about, those actuators that go up and down that move those individual mirrors side to side to compensate for a laser beam pointing towards a star in the sky. And as heat waves go through the atmosphere, you know, it gets colder and colder as we go up through the atmosphere. And we have heat disturbances that make the stars twinkle. And we call that scintillation. That scintillation can be corrected for with adaptive optics, where that laser beam can detect that scintillation or twinkling and can move those mirrors up and down just ever so slightly to get us that clearest picture possible. Now, what is the device that we use to image the galaxy and the star clusters and the nebula? We use what's called a CCD, or a charged coupled device. And this is a piece of silicon. The one I've mostly used was about the size of a dime, but there are some very large arrays, like you see here in picture B, that are a matrix of numerous CCDs to capture light. So a light photon, a particle of light, hits this silicon patch and it creates an electrical current that can be detected by the electronics for that detector and camera and telescope. And the number of electrons that we capture tells us how bright that object is. And we call that an electron well. So here we have a guy with a black bag over his hands, but in the visible we can't see his hands, right? But in the infrared, his hands are warm. His body temperature, 98.6 degrees Fahrenheit. And so the bag is cooler, it's the air temperature, we can see right through it and see his hands. And so infrared is what I use for most of my studies to see the cool but still warm stars against a very cold background of the universe. Now, we can split that light up, like we talked about in chapter 5, into spectra, and the device we use, whether it be a diffraction grating or a prism, is called a prism spectrometer. And so we spread that light out to be focused right here at the camera area, the detector, the CCD. But we can also look at radio waves. And so the first radio telescope was used by Jansky in this radio discovery of the Milky Way. Radio telescopes. And so this is a radio image of a black hole called Cygnus A. And we can see the black hole throwing away material on either side of the black hole that we can see at a 90-degree angle towards us. And we see this stuff moving away from the black hole. Pretty unique. All we would see in the visible would be the very tiny middle part of light being dragged into that black hole. And so this is the Green Bank Telescope. It's a fully steerable radio telescope in West Virginia. Went in operation in August of 2000, and its radio dish, or its listening ear, is about 100 meters across. Now we can combine radio telescopes into an array, and this is the Atacama Large Millimeter Submillimeter Array. That's the wavelength it's listening to, is the submillimeter in the Atacama Desert in northern Chile. And this currently provides the highest resolution for radio observatories, and this is run by the European Space Agency. Now we can even make radio telescopes even bigger than that by combining radio telescopes from around the world on one side of the Earth into electronically combine them into making the Earth as like it is one great big humongous radio observatory, and we have that with the very long baseline array. The largest radio and radar dish is right now in Arecibo, Puerto Rico, which has been greatly damaged by hurricane season of 2017. It's a 1,000-foot long radio dish filling in a valley, a natural valley here in Puerto Rico, with its detector being suspended up above by these 3 guide wires in a triangle series. We can also detect infrared radiation by getting away from a lot of the water vapor in our atmosphere. Our lower atmosphere is full of water vapor. That's where our weather is. But if we fly the specially modified 747 jet with a hole in the side of it with a telescope, we call this Sofia, the Stratospheric Observatory for Infrared Astronomy. And Sofia flies at about 55,000 feet or so at the limits of what a 747 can fly at, and it gets above all that water vapor in the atmosphere to detect infrared light. We have a great space telescope called Spitzer Space Telescope. You thought Hubble was the only one, but it's not. It's only one of several. And so the Spitzer Space Telescope looks at different types of spectra. These are X-ray images of the Flame Nebula, Cassiopeia A, and the Helix Nebula. These are all stars that have exploded at some point in the past and are now giving us what are called planetary nebula. It has nothing to do with planets, but we call them planetary nebula, and they're some of the most beautiful objects to see in the night sky. Now, the Hubble Space Telescope has done a couple of these images. This is called the Hubble Ultra Deep Field. This is a very tiny part of space, very tiny, about the size of a grain of sand held at arm's length. And this set of images were taken between September 24th and January 16th, 2004. And the images were collected on about a 40-minute exposure because the telescope's orbiting the Earth. So it has to keep its guide on the same patch of sky at the same time on one side of the Earth. And we stacked hundreds and hundreds of these images together to come up with this very amazing, unique image. And everything you see in this image here, every single dot and blemish, is a galaxy with over 200 billion stars on every single one. You can see some close to us here. Here are some spirals, some ellipticals, some irregulars. And these are all, every single thing on here is far, far away. And every single one of these is a galaxy with hundreds of billions of stars. The Hubble Ultra Deep Field. A buddy of mine who worked with me at Missouri State University when we were both high school students studying astronomy is now in charge of the Chandra X-ray Observatory. This is an X-ray observatory, the most powerful X-ray telescope in space. And they can see very high energy objects such as supernova explosions and gamma ray and neutron stars. Set to launch in 2019 is the James Webb Space Telescope. This is the telescope being built. It has undergone cryogenic testing. It means it's been brought down to the temperatures of deep space. And this telescope, unlike Hubble, which the space shuttle, which is now retired, of course, and put up in museums, could go and service every number of years it needed to, the James Webb Space Telescope is only going to be 1 million miles away from Earth at a very particular point in orbit to where it can point at a particular object for a continuous length of time. And we call these points in our orbits around the sun Lagrange points. And so this is going to be a telescope that has to work right the first time, which is why we've delayed it numerous years to make sure that it works right the very first time, because if it doesn't, that's about 15 to 20 years and billions of dollars down the drain. The European Space Agency is building the extremely large telescope in northern Chile, one of the driest deserts in the world, and without light pollution. And this is what a conceptual artist of it looks like. 39.3 meters across. That's a very, very extremely large telescope. And that's it for week 3, 5, chapters 5 and 6.